Well, welcome everyone to this this event in our Encode Algorand Education series. We're delighted to have Jay from the Reach team. Reach are pretty much integral to all things Algorand now, and probably very much the easiest and best way to start coding and building projects on Algorand. And Jay will tell you all about this. Encode, for those of you who aren't aware, is a developer community working across over 100 different universities around the world. I know a lot of you are from the various constituent universities, and a lot of you have done this whole series, which I think this is event 11, tempted to say. So we started months ago, and we're all the way here. And we'll be next month starts the Encode Algorand Hackathon, worldwide global hackathon for you to build an awesome project on Algorand. If you do have any comments, questions during the event, please do drop them in chat, and we'll get to them both during and at the end. We're also joined by Russ and Ryan from the Algorand team, who can answer any Algorand facing questions as well. Without further delay, Jay, great to have you, and looking forward to this event, and over to you, really.
Great. Well, thanks for having me, everyone. It's a pleasure to be here and talking with you all. My goal for today is to give you kind of a rundown about what Reach is and make sure that you know where you can go to learn more about it and to see the value in it. I'm going to assume that, as was mentioned, you've had a lot of experience. You've gone to 11 of these things, but I'm going to repeat myself a little bit. Sorry, I'm not going to repeat myself. I'm going to repeat what you probably already know, both about blockchain and about Algorand, just to make sure that there's consistency about what everything means, rather than me assuming that you think it means one thing, but it really means something else, etc. And I am extremely happy to answer questions as we're going. So please ask those through chat or by unmuting or whatever it is. Okay, so right now I am at the Reach documentation site, which is docs.reach.sh. Let me just open up something. So that is the site. It's docs.reach.sh. If you want to follow along or anything like that, then that's where you want to look at. I'm going to kind of describe what the documentation looks like before going into talking about what Reach actually is. So, Reach, as was mentioned, is a programming language for building dApps, and it works with Algorand and other chains. And it is designed to be an extremely high-level way of specifying the kind of dApp that you want to build, as opposed to needing to know the low-level details about the underlying virtual machine that the blockchain that you're using supports, or having to meticulously plan the state space of your smart contract as you design it. In other words, what I'm trying to say is that Reach is very emphatically a dApp programming language, as opposed to a smart contract programming language. It is designed to make it so you can build an entire dApp, where just one piece of that, of course, is the smart contract. Now, the way that we've organized the documentation is that there is a quick overview that gives you a sense about what Reach does and what it provides. I'll talk about that in a moment. We also have a tutorial, which is a long, directed exercise in building a particular program. And this particular program will help demonstrate the basics of writing a Reach program and the basics of what it means to be a dApp developer. One of our assumptions are that Reach programmers have familiarity with JavaScript, but they don't have any familiarity with they don't have any familiarity with blockchains or what it means to program a dApp or anything like that. Then there's what we call the guide, and the guide is sort of like technical blog posts about some big picture ideas about Reach. If you're curious about why things work a certain way, then often there's an answer inside of the guide, and other pages will link to things on the guide. Then there are what we call the workshop series. And the workshop series is essentially, if the overview is the day one of class and tutorial is your first month of class, the workshop are basically like the homeworks for class. They are a whole bunch of different example programs that you could build in Reach with some vague direction about how you might want to do that, so you can give yourself a task. And then finally, there's the reference manual. And the reference manual is an exhaustive look at every individual function that's provided by Reach, exactly how everything works. So there's lots and lots of detail. When you're looking for something, you can search the documentation. You can look at the index, which has an index list of every function and phrase that is defined anywhere in the manual in every section. And then there's also just looking at the table of contents right here, which can help you locate what it is that you're looking for. And then finally, we have a Discord community for Reach developers. I'm going to post a link to that in the chat right now. So please join that to learn and talk about Reach. While I was talking, someone asked the question, what other chains does Reach support? So ReachNet right now supports Algorand, and we support Ethereum, we support Conflux, and we support a number of different EVM-based chains that provide an EVM compatibility layer. We are building support for multiple other chains, and our overall mission is to make it so that we have a common platform for dApp developers to collaborate with one another and build their products, regardless of what chain they ultimately deploy to. One of our sort of mission statements is that we want to try to remove the silos and tribalism that is in some parts of the blockchain world by making it so that people can collaborate to build the kinds of projects that people care about, because we think that in the long run, blockchain will be successful based on customers, and customers will primarily care about the product, not the chain that it runs on. My mother doesn't care that her phone runs on an ARM chip. That's not even something that she even thinks about. She, in fact, doesn't even really know what the difference between an Apple and an Android phone is. So I think that consumers are likely to think that way. There's also a question, can I use more than one chain with the same dApp? The answer is yes, but make sure I understand what I mean. So when you write a Reach program, when you compile that program, you get an Algorand version, and you get an Ethereum version, and you get a Conflux version. You get each one of those versions. So that means that your one program you can take those versions and deploy them on multiple different chains and use them. Now, a question that you might have is, if I write my Reach program and I have my Algorand version and my Ethereum version and I launch those, can now those two programs like talk to one another? Does this mean that now it's like the same program running on Ethereum and Algorand, and now they can collaborate cross-chain? That is not a current feature, but that is a feature that we have ideas about how to implement, and that is on the roadmap. And if you write in Reach today, then you'll be able to do that in the future. Now, I've given you the brief overview of the documentation. Now I just want to talk a little bit more about what it really is like to program in Reach. And so I want to say something about the kind of the material that's on the overview. So the first thing is that when we talk about dApps, we mean something more than a smart contract. What we mean, from our perspective, what a dApp is a smart contract that runs on chain, a middleware layer that interacts with that smart contract, and then front ends that actually interface with users. This is the sort of very standard 3-tier architecture that we see in common web applications, where you have the client that runs in the browser, you have the backend web server, and then you have the web server that's in the middle, and then you have a backend database. Essentially, what blockchains do is they provide a database that is a globalized database, and that database has smart, trustworthy stored code, which are what the smart contracts are. And your middleware layer, rather than running on a centralized server, is now something that runs locally inside of each client. But there is still value when you develop your application to have that middleware layer be abstracted from the user interface of the front end. And so from our perspective, a dApp is made up of all 3 of these components. And when you write a Reach program, you are writing the second 2, the database and the middleware layer, i.e. the smart contract and the middleware layer. You're writing those simultaneously. When you write a reach program, we analyze your program and we extract out a smart contract that enforces the rules of your DApp, and we extract out the behavior of each one of the individual participants. Now, when you're writing those two programs simultaneously together, where they're meshed, you are also specifying the interface that this middleware provides to a front-end server. So in some sense, you're actually saying something about all three of those pieces. You are implicitly saying how the smart contract will work. I say implicitly because if you look at a reach program, there's no point at which you say, aha, that's where I wrote the smart contract. Instead, you describe a computation, and then when you write that computation, we derive a smart contract for it. You're also specifying the behavior of those middleware layers, and you're specifying the interface for the front end. While I was talking, there was a question about will there be reach support for Vim and NeoVim? So if you look at the guide, then there's a chapter that is called IDE and Text Editor Support. And right now we have support for Visual Studio, which is quite well supported. And we have Atom and Sublime. And I personally use NeoVim. So what I do when I use NeoVim is I just set reach files to be JavaScript, and it basically works. But behind the scenes of these IDEs is a language server protocol implementation, an LSP implementation. And one of the things that we will do in the future is document how to use those LSPs in other editors like Emacs and Vim. And so anyway, so if you are an Emacs or Vim user, jump on the Discord and ask me, and I'll tell you the tricks to setting it up. Okay, so I've given you kind of a brief idea about the perspective of reach. Now, what does that really look like? So this right here is an example of a very small reach program. So in this reach program, there's a few things to say, which is that when you write a reach program, you are literally writing JavaScript syntax. This is on purpose to make it so that it's as easy to pick up reach as possible. And essentially, when you're writing reach, you can kind of imagine that you're basically using like a weird JavaScript library. Now, you're not literally using a weird JavaScript library because we have our own completely separate compiler that's completely detached from JavaScript, but the syntax is very similar. And so because the syntax is similar but different, we say that at the beginning of a reach program, you say what version of reach you're using. And the main component of a reach program is you're going to export a reach application. And so reach.app is a function that you give another function to, and inside of that you specify all the steps of your program. One of the main things that you do is that you're going to be specifying who is going to be involved in your program. These are called participants. Each one of those participants are going to be one of those middlewares that I talked about before. So in this case, this program is going to have a participant named Alice, and inside of this object right here, we specify the front-end interface. Remember I talked about these three components, the smart contract, the participants, and then the front-end interface? You see that right here, because we're saying, here is the fact that there's one participant, here's another. This participant's front-end provides these functions. This participant's front-end provides these functions. And then once we've set up the context of this application, we can deploy the application and actually write down what the steps of the computation are. We go down, we can see here's an example of some of the steps. One of the main kind of ideas about reach is that you're writing the program with everything that happens interweaved together. So you're saying, here are the stuff that Alice does, here are the stuff that Bob does, or maybe we're to take another example of, here are the stuff that the liquidity provider does, and here's something that the trader does. And we say what all of those things are at the same time. And then what we do is that what the reach compiler does is it separates those and it turns them into each one of those artifacts that I talked about and guarantees that the assumptions that one makes are met by what is guaranteed by the other side and vice versa. Those assumptions that are generated automatically and checked automatically, that is basically the work that Reach is saving you from doing. When you design a DApp, if you weren't using Reach, you have to implement each one of these things. You have to implement the smart contract. You have to implement the behavior of, say, liquidity providers. You have to implement the behavior of, let's say, traders, and you have to implement the front ends. And each one of those things has assumptions about how the other ones work, and they all have to be in sync with one another. And that's normally something that you do manually, but with Reach, it's done automatically. And so this idea that you write things weave together. You can see that in this little excerpt of a reach program. We say that in this program, Alice is the only one that takes this step, and then she's going to publish information, and then we're going to commit to that. So this right here is kind of the 3 steps where individual participants can do things entirely locally that are not verifiable. Then they can share that information with the entire world. And once they get shared, we can check to make sure that they have provided values that fit the assumptions of everybody else. So I'm not going to go into the rest of this program. You can look at the overview, but I just want to kind of talk a little bit about it. Now, as I mentioned, when you compile a reach program, you get these different values. And now the next thing is that reach doesn't just compile your program, it also verifies that your program doesn't have huge categories of errors. And so every time you write any reach program and every time you compile it, it will always be automatically verified with a theorem prover. And if there is a mistake, it will abort the compile and it won't allow you to run your program. And so what this does is it guarantees that your program is not susceptible to the kinds of attacks that we constantly hear about in the blockchain world. I'll talk about this verification procedure a little bit later. And then when you build a reach program, you also have to write those front ends. And so reach provides a standard library for making it easy to make those front ends in JavaScript, Python, and Go. And we have ways of supporting other languages too, if you're interested in other particular languages. Finally, reach provides a runtime support system for you to run automated tests of your programs. So you probably know about the concept of a DevNet, where when you're developing for a blockchain, you will often run a sort of private node with its own little private network. And when you use Reach, it will automatically create one of these for you every time you run your program automatically to make it so that each test instance is insulated from all of the other ones. And that's sort of like a fundamental step when you're building and using Reach. And finally, those front ends that I talked about, you can, of course, build those with any JavaScript code that you want, meaning, of course, that you can build them with GUI frameworks like React and Vue and whatnot, and there's a wide variety of those implemented for Reach. So if you want to dig in, then checking out the overview is a nice summary. I'm going to switch now and talk a little bit about the tutorial, but while I was talking, there was a question. So someone asked the question, is Reach a private company or a decentralized protocol? Reach is a private company, and there is no protocol associated with Reach. There's no token associated with Reach. Reach is not a blockchain. Reach is a development platform. We kind of think of ourselves as being the operating system for decentralized applications. And what that means is that when you use Reach, it is like saying that I use Java or that I use JavaScript or Node or something like that. We are not our own blockchain network. You use Reach, and then you can use pretty much any other network. I mean, of course, there are networks that we don't support yet, but we don't support them not because of some principled reason. It's just that we don't support them because they haven't, we haven't ported to them yet. So yeah, so there's no token or anything like that. If you want a more explanation of that, 12345A, I'll elaborate. Also, Kevin McGill asked the question, is a JavaScript framework required for the front end? No. So people have written, I assume, by the way, there's sort of two questions you could be asking. Do I have to write the front end to JavaScript? No. We have examples of writing it in Python and Go. Now, the next question is, if I write a GUI version, like a web interface, do I have to use a framework like React or Vue or one of these other ones? Can I just go frameworkless? And of course, the answer is yes. You don't have to use any particular framework. We just demonstrate in our examples using React because it's very easy to make a really short example in React. But we have examples of frameworks and unframeworked and all sorts of different JavaScript styles. All right, if there are, as always, continue to ask questions as we're going. I now want to talk about our tutorial. And we've now been talking for about 20 minutes. And I would say that hopefully I've whetted your appetite. And I want to kind of, like, my call to action for you is that when we hang up this call, choose a time that you are going to go through the tutorial and go through the whole thing for yourself. And when you do that, you're going to be able to learn a lot more about Reach. And of course, I'll show you it really running in a moment. Okay, so the tutorial walks you through how to actually install Reach. And Reach is a Dockerized program. And what I mean by a Dockerized program is that you essentially need a Unix environment, and you need to have Docker installed. And if you have those two things, then you don't need to have any other program, any other prerequisites. Everything else will just work. Now, if you got scared off by a Unix environment because you're on Windows, don't worry, because we support Windows very well. You can use the VS Code IDE to interact with it. And then also every Windows computer now has WSL on it, and WSL is an amazing way of having a Linux computer inside of your Windows. And I am on Windows, so the main developer of the project is a Windows user. And our testing infrastructure is all on Linux, and then all the developers other than me are on OS 10. So all of your platforms, we support them. Yeah. Okay, so you have a very basic thing that you need to have installed. And essentially the way that you install Reach is that you download it from our Git repository. Let me just go over here and do that. So we download it from our Git repository, and then now we can run Reach. And I'll just write run Reach version down here. You'll see that, okay, I'm using Reach version 0.1. And you can run Reach update. And what that's going to do is it's going to make sure that all the Docker containers that Reach uses are downloaded on your machine and up to date. You can do this regularly, and they will get updated. You can see that it is downloading new ones for me because I typically run the development version, so I don't actually have the Docker images installed. So while this is doing something, I'll talk a little bit. Okay. Next, I want to talk about getting started. What the tutorial walks you through is writing a really simple program. Now, when you're teaching somebody to use a tool, you can talk about the tool, and you can also talk about what you build with the tool. And sometimes the thing that you build with the tool is complicated. So as an example, I think that it's very intuitive to want a house. So if I were to teach you how to use a hammer to build a house, then you'd be like, oh yeah, that makes perfect sense, because I know what a house is. In contrast, if I were to tell you how to use like a machining tool to make a gasket for an engine, you might say to yourself, what the heck is a gasket? Why do gaskets matter? And then I'm gonna have to teach you about what gaskets are, why they're useful, why they form this fundamental piece of an engine. And maybe it would be better if I were to teach you machining to, like, I don't know, make like a keychain or something like that, because you're going to learn the fundamental tools of using the fundamental attributes of using this tool, but you don't have to also learn this complicated problem that the tool exists to fix. So similarly, when you're learning about dApp development, it's very common for attempts to teach you to force you to learn about what dApps are for. And so that's where you'll learn about complicated ideas like DAOs and liquidity pools and decentralized exchanges and stablecoins. And they're basically these vogue concepts of what people think that would be exciting dApps to build. And they're often very foreign to sort of normal everyday pursuits. So what we try to do in the Reach tutorial is go in a very different direction from that. Instead of teaching about some complicated dApp problem, we want to focus on a really simple problem that everyone understands, which is that there's a game called Rock, Paper, Scissors, and sometimes you can bet on the outcome of this game. So that is the problem that the tutorial gives you. If you don't know what Rock, Paper, Scissors is, in other parts of the world other than the West, it has different names. So there's like, but basically the idea is that there are 3 symbols that you hold out with your hands. There's rock, paper, and scissors. And there is a simple connection between, there's like a dominance hierarchy between these where scissors cuts paper, paper suffocates rock, and then rock smashes scissors. So that's all you need to know about the rules of rock, paper, scissors. And we could wager on the outcome of that. So the tutorial walks through is how to make that game. Now, while I was talking about the previous thing, someone asked the question, how does reach compare to solidity? What are the trade-offs? This is a very deep question. And we do have a section of the guide that talks about this. So if we go to the guide, there's a section that says, how does reach development compare to solidity development? And there's a lot of deep explanation here about how this could work, where I talk about what are the components of doing, of making a reliable dApp. And I talk about how there's basically sort of 7 things that you want to do when you're building a dApp. And if I were to tell you I'm using Solidity to build my dApp, really that's only talking about a very small part of the entire picture of building that dApp. I'm really only telling you something about like step 2. I'm not really telling you about all the other components of building the dApp. And that's why people who use Solidity also use other tools like Truffle, and they use a large variety of tools. In contrast, a lot of the things that are pieces that are done disparately when you program with Solidity are done in one place when you use reach. And that's what this document talks about. So if you are already a Solidity developer, it would be a great thing to read. On the other hand, if you are not already a Solidity developer and you want kind of a much higher level pitch, is that when you run in Solidity, you are limited to only working on EVM-based chains. So that means that there's a huge number of up-and-coming chains that you can't work on. You can't work on Algorand, where the transaction fees are extremely low. You can't work on other networks like, I don't know, like Polkadot or Conflux or Tezos or Solana or Cardano. So there are a large number of other networks where the lingua franca of those networks is not EVM based, so you can't use Solidity for those. So that's sort of thing number 1. You're not blockchain agnostic. Thing number 2 is that when you write a Solidity program, you're writing only one component of the entire dApp. Remember, the dApp is the front end, the middleware layer, and the smart contract. And when you write in Solidity, you're only writing in that. You're only making that smart contract. The next thing is that when you write that smart contract, when you use Solidity, you have a very complicated design problem of laying out the state space of your program and making sure that the state transitions that you program in are valid and do what you expect. And that's a very complicated thing to explain exactly what that means. But basically, you can kind of summarize this as that Solidity is a low-level programming language and Reach is a high-level programming language. It's intuitive to people that programming in Python is easier in some way than programming in C or assembly. And so programming in Reach versus Solidity is a similar level of easiness. That also tells you what some of the trade-offs are, because these things that I've talked about so far are like this, because maybe you don't want to work on Algorand and you want to make sure that your program only works on Ethereum and does some really specific Ethereum thing. Well, that's not going to be possible to do in Reach, and that's on purpose, and we're totally okay with that. Our mindset is that if only 95% of all applications are written in Reach, that would be great. We don't need to have 100%, just like even today, when we have amazing programming languages like Python, JavaScript, and C, if you program in JavaScript, sometimes you write part of your program in C. And if you program in C, sometimes you write part of your program in assembly. That's just the way that the world works, where sometimes you need to have really low-level specifications of part of your program. The next thing is that when you program in Solidity, you have no guarantees that your program has that is missing certain categories of errors, because Solidity has no built-in automatic verification, and getting your code audited and verified is a fundamental step of writing in Solidity that just is not part of the game in Reach, because it's automatically verified. So those are some of the things that are different. We could say more. Someone asked us a question, is Reach the recommended language for building Avalanche applications now? We don't have a relationship with Avalanche. And if you instead you were asking about Algorand, is Reach the recommended language for building Algorand applications now? I would say that Algorand is evolving to the point to have a core high-performance virtual machine, the AVM, where the AVM is designed for these low-level, highly optimized programs, just like the x86 processor is optimized for low-level programs that can be a powerful compilation target to other languages. And right now, Reach compiles to the AVM, and we hope that in the future, other languages will target the AVM too. But right now, we're the main language that targets the AVM. I think that you could interpret that as being we're the recommended language, but we are a great language for writing dApps, and writing low-level programs is also great in all of the platforms that we support, if that's really what you need to do. And that Algorand is no different from that. Okay, so leaving aside the questions and coming back to the tutorial, we talked about how we can install by downloading from GitHub and making sure that everything's updated. And we'll know that we have everything ready when we can write Reach compile version, and it will tell us, aha, this is the version that you have of the Reach compiler. Now, when we write a Reach program, we are going to be writing two different, well, when we write a Reach program, we're writing one file. This is in a .reach program. And when we build a test program, what we do is we also write an automated testing JavaScript program. So what I'm going to do is I'm going to, let me just move this to the side. I do this. I'll move this one. Okay, this is good. I'll have it like this. So I'll have them both open at the same time. All right, so I'm going to edit this. So I'm going to write this Reach program out. Or write export const main equals Reach app. Maybe I should make it so that it's formatted exactly like it's on the page. So I'll say who the participants are. There's Alice, who doesn't have any options, and then there's Bob, who also doesn't provide any functions. And then we write AB goes to exit, and then we're good to go. Okay. Now I'm also going to write another program, which is the going to be the testing program. And so this one I'm going to copy because it's a pain to write all that. I copied all that. And now I've got my little program. So how do we actually run the Reach program? Well, I come down here and I run Reach run. And when I run Reach run, it's going to go compile the program, which also verifies it. And it's going to go start up a DevNet. And it's going to have that DevNet run this particular program, start up a node for it. In this case, it defaults to an Ethereum node and then runs it. We can instead run with an Algorand node by writing Reach connector mode equals algo. And then now what it'll do is it'll start up an Algorand node for testing instead of an Ethereum one. And this right here is basically what your life looks like when you're programming in Reach. You're working on a Reach program, you're working on an automated test suite, and then you're running example programs, example instances of your test program. Now, maybe you're not running Vim, and so maybe you're running it in VS Code where you have different tabs or something like this, but this is kind of what your life is like. As I said, I don't want to go through the entire tutorial with you here. I just want to kind of give you kind of the high points about where we go. And so because of that, what I'm going to do is I'm actually going to copy the code from a certain point in the tutorial. So here, we'll copy this code from the step that we're on, step 3, and we'll copy the front end, and we'll copy the Reach file, and we'll copy them here. So let's reload these files. Okay. So now when we reload these files, we can see that the Reach program has expanded. What I've done is I've made it so that each of the players of the game who have the names Alice and Bob, which are sort of like common prototypical names when you're talking about cryptographic protocols. They both have the ability to return the hand they play in the game and see the outcome of the game. And so we first have Alice, that backend requests from the front end, what hand are you going to play? And then it publishes it to the world. Kind of the mental model that you have when you're writing a reach program is that there's this like universal computer, and this computer is guaranteeing that everyone is following the rules of this program. And in this case, the rules are that Alice goes first and publishes a number, and then we check things about it. In this case, we don't actually check anything. And then Bob goes next, and he publishes something, and then we compute a value that everyone agrees about what those values are. And then we're done. And then now, because everyone saw the exact same hand A and hand B, they will all see the exact same outcome of the game. And so this is a really simple version of rock, paper, scissors. There's no actual wager yet. And then when we go down and we see the program, let me just sort of talk through the example front end, which is like an automated test suite. We require the reach standard library. And this, by the way, is just normal JavaScript. We require the reach standard library. We require the compilation output. We load the standard library. We turn the human readable number 10 into whatever the internal currency of the network that we're using is. So this would, for instance, turn a 10 ETH into Wei, or it would turn 10 algo into micro algo, etc. We then create test accounts that each start off with 10. We have Alice deploy the contract. We have Bob attach to the contract that Alice deployed. And then we run the game where we simulate running Alice. Well, no, not simulate it. We run Alice and we run Bob, both from this from threads inside of this JavaScript program, where each one will randomly decide what hand they play. So when we run this program, let me just go up and do reach run. We see that it first compiles the program, starts the devnet, connects to the devnet, and we see that Alice played paper, Bob played scissors, and then they both agree that the outcome of the game is Bob wins. This fact that they both agree on the outcome, this is why consensus networks are called consensus networks, because they allow many people inside of a computation to reach consensus about what happened in the outcome of the game. Now, if you look at this program, there are a few little details that you might see. So some things appear kind of obvious where, hand A is defined right here, and it comes from calling the getHand function. And we call getHand on this object called interact, which is how we interact with the front end. But then there's this other thing right here called declassify. And so Russ asked the question, what does declassify do? So one of the things that Reach does is it guarantees that secret values stay secret. And so what that means is that any information that a participant is the only one that they know about is secret and will not be shared unless it is explicitly declassified. So this is a common security information flow analysis that you do in programs where, if you have secret information, you can basically have the assumption that like either things start secret and then they become public, or they start public and then they become secret. Well, clearly it's more secure for things to start secret and be explicitly declassified than to start public and be classified after that. And so the operation in a reach program that allows information to be exposed is called declassify. So this says that I explicitly want to allow the value that comes from this to be shared. And so I'm going to declassify it, and then it will ultimately go out. So when you're normally programming in like JavaScript or Python, you probably think that, okay, well, if I were to look at a variable in the program, there's a value like 5, and then there's like a type like number. And so that means that everything in your program has kind of these two properties. There's like, what's the value? And then values have types. Well, in Reach, things in your program are values, which have types, but then the value, it's not just a value, it also is a secrecy level. And so the secrecy levels are public, private, we're really private, public, and then shared with everybody. So things start off private, they become public, and then they actually become shared with everybody. So there's just kind of different steps that things go through. Someone asked the question, what is the biggest project written in Reach? There's kind of two ways to answer that. There's like, what is the biggest program that like, Reach ships with? I actually don't know the answer to that. So it looks like the largest program that's in our repository is a test case that someone sent me that's 450 lines. So that's the largest one that is just like sitting around in our program. That's pretty big. I think that what that one does is it does inventory tracking of it basically is like an ordering system where it will like guarantee that like taxes are paid properly or something. I actually don't really know what it does. I just know that it had a compile error and I fixed it. And like that program, for instance, if you were to have written that program directly in Solidity, then now it's B. Kind of similar size, not 800 lines. And if you were to have written that one in Teal, then you're looking at writing like 2,000 lines of Teal code to write that program. So that's kind of a big program, and that's just literally picking like a random program that's a big program. But if you want to sort of get a sense of what kinds of programs people have written in Reach, then what I would recommend doing is looking at YouTube Reach. So your reach.sh. So if you look at our YouTube channel, then you can see these. So we run a regular bounty hack program where people write programs and talk about them. And so you can watch these videos where people will talk about the kinds of programs that people have written. So like, here's someone talking about writing the game Battleship. Here's like a crowdfunding program. Here's an NFT auction. Here's an insurance program. This is a censorship-resistant microblogging platform. This one right here is what's called an optimization market, where basically you provide a function and you want to pay whoever can figure out the best solution to that function. So this is a way of basically like abstracting computation resources. So rather than like buying a computer that you run an optimization algorithm on, like for doing computational fluid dynamics, instead what you do is you publish the problem and then you pay whoever figures out the best solution to it. So it's a way of paying for results as opposed to paying for computation. So anyway, so there's lots of interesting programs that people have written, and in our Git repository, you can look at many examples of interesting things that we do. And all of these things, by the way, are talked about in the workshop. If you look at the workshops, you can see, well, not all of them, but you can see many programs, that are interesting programs that people care about. All right, so I've just kind of given you a brief sense of what this program looks like, and I want to kind of skip ahead to this little chapter about finding errors in programs. So let's go to, actually, let's skip to this one. Okay, so I'm skipping to the code that's from step 7 of the tutorial. The code has become more elaborate, where some of the things that we do in it are we abstract the implementation of the game and we verify that it works correctly. We also make it so that our program has a wager, and we actually have Alice post the terms of the wager and Bob agree to them. We do things like guaranteeing that if one side of the game stops playing, that the other side can come and take the money that they have escrowed back, so it's not locked away forever. We make it so that the game continues playing until there's not a draw. So you basically keep playing until someone wins. We also use the cryptographic commitment pattern to make it so that whoever publishes their hand first, the other side can't look at it and figure out what they need to do to win. And then when we're done, we send off the proceeds to the winner. And the front-end program is almost actually exactly the same, because all we've just done is add some extra printout messages to show that a certain person won. So they just run the program and you'll see they're run. Okay, but what I wanted to show is, and by the way, this program right here, it's an 88-line program, but this is an extremely dense program. Again, if we were to look at what it takes to write this program in another language, oops. So if you were to write this in Teal, you're looking at like 2,000 lines of code. And if you were to write it in Solidity, then you're looking at like, 400 lines of code. So I mean, maybe you're not scared of writing 400 lines of Solidity, but it's certainly easier to write, 88 lines of very, very high level reach than to write 400 lines of Solidity. So anyways, so one of the things that's special about Reach is that it will automatically check to make sure that your program doesn't have certain kinds of errors. So here's an example of a kind of error that your program could have. Tell me if you've heard of a program that does this. It accepts a whole bunch of money, but there's an error in the program, and now some of that money is locked away forever and can never be accessed because there's no way to get the program to release it. Programs like that have been launched on Ethereum, and they have literally lost, millions of dollars. Well, we can actually experiment with what would happen if we made our program have this error. So right here in the program, Alice pays in the wager, and Bob pays in the wager right here. So that means that the wager goes in 2 times. So it goes in 2 times. So that means that the balance of how much money is in the contract is 2 times the wager. And then right here, we send out 2 times the wager to whoever does this. Now, what if I change this to 3 times the wager? This program is bad. It's bad because I don't have 3 times the wager. That means if I tried to transfer it out, it would not be possible to transfer it out, and thus the program would fail, and thus no one would get the money because you can't access it. Now, if I run reach run on this program, the compiler is going to tell me that no, it's actually not possible to do this. It says that on line 83, which is this line of the program right here, 83, there was an assertion that said that the balance is sufficient for a transfer. And it says that there is a theorem formalization, and this theorem formalization says that 3 times the wager must be less than the balance. And the balance could be 2, and the wager could be 1. And since those 2 things are what it could be, that means that this is false, because 3 times 1 is 3, and that's not less than 2. So therefore, this theorem is false. So it refuses to compile our program, and we can't use it. Let's look if we made the mistake in the opposite direction. What if we tried to transfer too little money? Well, now when we run the program, we're just going to get a different error. This error is going to say, on line 88 of the program, what's line 88? It's this line, it's the last line of the program. On line 88 of the program, it says that there is supposed to be a balance 0 at the application exit, which says that we have to prove that 0 is equal to the balance minus the wager. And the balance could be 2, and the wager could be 1. Now, why does it say balance minus wager? That's because, well, we know that the balance is what the total amount is. And then this right here, it says we transferred 1 wager away. So that means that this right here is what the current total wager is. So that has got to be equal to 0, and it's not. So when you write a reach program, it will automatically check to make sure that your program doesn't have mistakes that are related to general blockchain properties, like what's called token linearity, which is this one. It also guarantees that your program doesn't have other kinds of errors that are ones that are specific to exactly what your program does. So anyways, I think that this is a good summary of what reach is and how it works. And you may have noticed that I didn't really talk very much about the fact that you're doing all this in Algorand. And that's because it's actually not really relevant that you're doing it in Algorand. When you're actually writing the reach program, you don't really think about what network you're using. You're just writing a reach program. Now, when you ultimately decide to deploy it, that's when you decide, okay, well, I'm going to take the Algorand version of the program, and that's the one that I'm going to deploy. I'm going to take the Ethereum one. And, I think that almost everybody wants to use a platform where the transaction fees are low. If they're building a dApp that is not purely a DeFi application. And the reason why is because your use of the consensus network is only incidental to the reason that you're using a program. So you don't actually really have network effects that are relevant for what you're trying to do, because you're trying to, let's say, raise money for crowdfunding, or you're trying to, have an auction or something like that. Those things, there's not really strong network effects for why you would prefer one platform over any other. It's only in DeFi applications where you're actively trading, existing tokens on some other network that you would even care about what network you actually use. And so in that case, I think that it's very valuable to be able to choose a low transaction cost network like Algorand and not have to learn how to program the low level thing. Someone asked the question, how many reach users are there out of interest? So if you go to Discord, you can see that we got 826 Discord members, about 1,000.2 followers, and then there's a whole bunch of YouTube subscribers. So that's kind of a proxy for how many there are. And I think that the last time we checked, there's like a little over 1,000 or like 1,100 people who like compile regularly and like update regularly, because obviously when you update, it like contacts the network, so we can see how often people do that. Oops. This is a really big window. So if I go back, there we go, reset. We'll go to Docker Hub. This is kind of a nice way you can tell. So you can see that there's been 2.6 thousand downloads of there's been 8.1 thousand downloads of the runner package that you use when you run your reach, when you run a test program. There's been 10,000 downloads of our DevNet. So anyways, that's kind of that gives you a sense about how many users there are. So anyways, so that's all I've got to talk to you about right now. I'm happy to answer questions for a while. Russ asks, when running testnet, is there a way to determine the actual account to dispense funds when insufficient? Is to turn on the debugger. Oh, sorry, is the way to determine the actual account to dispense funds when insufficient is to turn on the debugger. Okay, so if we look at this example program that I've been talking about, it uses this function called new test account. And new test account, what that does is it creates a completely fresh account. Because all of these networks, by the way, you can just make accounts by just generating random numbers. So it just generates a random number, makes that an account. And what a test account means in Reach is that we're going to take money from the quote faucet and send it to this account. And a faucet is a concept that's basically like someone who's willing to give away free money. Now, when you run with Reach Run by default, it starts up a private DevNet, and that private DevNet has a faucet that Reach knows about and can take money from that. If in contrast, you were to test your program on the testnet, meaning like the one that like, let's say Algorand runs, or if you're talking about Ethereum, like Ropsten is an example of a testnet. If you were running on a testnet like that, then you would not want to use this function, because those faucets are not scriptable, so there's not a way to automatically send it the money. Instead, you would be using a different function. So if I go down to the reference manual and I look at support for writing front ends, and I want to write in JavaScript, and then I want to look at accounts, then there's a bunch of functions. So you can write get default account, and what that does is it like contacts your wallet, so like MetaMask or AlgoSigner or something, and gets your account. If you do new account from secret or new account from mnemonic, that is like loading an account, like loading a wallet that you trust Reach to deal with. There's new test account, which is going to load a test one. And then there is create account, and create account would create a totally new artificial one. Essentially what new test account does is it just calls create account, and then it calls fund from faucet. So basically what Russ's question is if I'm running on testnet, how do I know what account to transfer to? Well, you probably would have made this account through either the default account, which means that your signer tells you what it is, or you did it from a secret, so that means that you know. So basically in those two situations, you know what the account is. The only way that you didn't know what the account is if you had to create the account, in which case, then you would just call the get address function. So the get address function returns the account's address as a string, and then now you know what it is, so you can print that out and send it to it. Kevin asked the question, how are programs upgraded on the network? So Reach does not support upgradable contracts. So there's no feature inside of Reach that says, I compiled this Reach program, and then I changed the Reach program in some way, and I compiled it again. And now I want to take that new compiled version, and I want to go change the old, something that's already been deployed. So upgradable contracts are a very interesting thing, and we're interested in adding that feature in a way where we can verify it. Scalar asked the question, how will Reach change with the new Algorand virtual machine? Will the new features be live soon? Can we expect new features? Yeah, so Algorand is launching the AVM version 0.9 shortly. And soon after that, they'll be launching AVM 1.0. And those new features, like we work at Reach extremely closely with Algorand to figure out what are high priority features for the virtual machine to support. And a lot of what those AVM features are going to do is make it so that Reach can generate better code. And because if it can generate better code, the way that translates into things being better for users is that, like right now on Algorand, there are limitations on how you write your program because to get very high performance, and some of those limitations are being relaxed, and the virtual machine is becoming more powerful so that you can do more stuff inside of those limitations. And so what Reach does is it insulates you as a programmer from what those limitations are fairly well. But occasionally you will write a Reach program and the compiler will say, sorry, I can't make this program work on Algorand. And when the new AVM features are launched, we'll be able to use those to compile better. And so I don't think that there are any things that the new AVM features actually make possible that aren't possible already. But essentially it just makes it so that we can do them better. In the long run, though, there are going to be some things that are going to be part of AVM that will be truly new features. But right now, the short-term ones in 0.9 aren't in that category. In general, I would say that if you write your program in Reach, then it'll work today. And when the backends that we support get better because the networks get more powerful, then you'll be able to use those new features too. This is the value of using a platform that insulates you from the hardware. Just like if you were to, write your software, targeting C and Linux, it's going to work on more machines and work better than if you wrote it in assembly, that you don't need to rewrite it when, the underlying machine changes. Someone asked the question, do I need a Reach auditor if I build a dApp with Reach? There are certain things that auditors do that are not really necessary when you use Reach. For example, a good auditor, one of the things that they would do is they would check the token linearity property for you. Well, Reach checks the token linearity property for you automatically. In general, what Reach does is it gives the kinds of powerful tools that great auditors use to normal developers to use in a way that looks like normal programming. That's the way that we approach verification. Verification should look and feel just like normal programming so that normal people can do it. They don't need to be verification and auditing experts. So in that sense, there are some things that an auditor would do that wouldn't be necessary in Reach. On the other hand, you know, Reach can only check that your code works. It can't check if you wrote the right code. What I mean by that is that suppose that you wrote a program that was supposed to add two numbers, but it actually multiplied them. Unless you add additional assertions into your program that specify that, you know, when you send in 1 and 2, you're supposed to get 3 and not 2. Like unless you say more information, then Reach is not going to be able to check that. And so what a Reach auditor would do, a great one, would be to check to make sure that you included the right assertions. So kind of a way to think about this is that if I have an auditor look at my Solidity program, what they are going to do is they are going to prove that my program is correct by doing their own analyses, but they're not like checking my work. They're actually doing the verification. In contrast with Reach, you do your work, the Reach compiler verifies it, and what an auditor would do is basically say, did you tell the Reach compiler to do enough stuff? And one of the things that's advantageous about this is that imagine that you pay the Solidity auditor, and then they verify your program, and then you change your program. Well, guess what? That audit is meaningless because the audit was only for, you know, version 2 of the program, and now you're at version 4, and now the program's different. In contrast, a Reach auditor would say, you should add assertions A, B, C, and D into your program. And now once you add them, Reach will verify those every single time you compile after that. Remember I showed you that big long program, the tax thing? I think that program contains like 800 verification claims in it that are all checked every single time you run by Reach. So auditing is actually more valuable in that sense in Reach. And so anyways, there's a role for auditing in Reach for some things you don't need to do. And you know, I think that in the DApp space, people audit as much for technical reasons as they do for marketing reasons, and using Reach doesn't really change that marketing calculus. David Jimenez asked the question, what's the current capacity to make transactions or contracts per second of Reach's blockchain? So as I mentioned before, Reach is not a blockchain or a network or a protocol or a token or anything like that. Reach is a platform that deploys on other networks that already exist. And so we support Algorand, Ethereum, and a variety of other chains. And so there's no, like, the limitations are the limitations of the network Reach deploys to, not to Reach itself. Reach is a way to make you faster, not a way, it makes you as a developer faster. It also turns out to make your programs faster because it can do optimizations that are kind of infeasible to do by hand, but yeah. If there are no more questions, I believe that we are, sorry. Kevin asked the question. Maybe I'll answer this one more question, Anthony, and then we'll end. So he says, if programs are immutable, then I'd assume existing contracts would execute as intended, but my front end should start using the new program to introduce new features or changes. Yeah, that's a great way to think about it, Kevin. So, you know, in that way of thinking about things where you have the front end, you have the back end, and then you have the smart contract, there's no reason to say that the front end can't know how to communicate with different backends and different smart contracts, because the front end is like the user interface. A little example of this is like when you use an email client, your email client probably knows how to speak the SMTP language, which is like the really old way of dealing with email. It probably knows how to speak IMAP, which is like a more modern way of doing it. And maybe it even knows how to speak the Outlook protocol or the Gmail protocol. And so there's a wide variety of different ways to interact with email clients. And so a front end that worked for dApps, it is very reasonable to imagine that it knows how to speak to different kinds of dApps. For instance, dApps that are like this one, but they're the one that we used to use. And now dApps that are like this one that are the new one. So the front end could include all of that behavior. But that's all possible. But I would say that it is definitely on the roadmap to support upgradability in Reach, but not to mandate upgradability, because not being able to upgrade is actually a feature for some people, because if I can upgrade, then that means I can change the rules on you. And that means that you now have to trust me more than you would otherwise. So actually promising that you can't change the rules is in some ways a feature. So anyway, so right now that's the state where it reaches, where there's not really an option for upgrading, but we intend to support this.
Excellent. Well, Jay, thank you very much. That was an absolute privilege. I certainly learned a lot as well, and I know the students and the devs who joined us today very much enjoyed it. So thank you very much for your time this evening for us, this morning for you. And hopefully we see lots of Reach-built applications in the hackathon next month. And we'll yeah, definitely be encouraging the guys to do so, and girls. Well, thank you everyone for joining. We'll stick the, there's no slides here, so the video content will be the main content, and then that'll go up, we hope, tomorrow morning. Jay has very kindly shared the Reach Discord as well, if you want to go and ask, and the docs, if you want to go and ask questions there. Well, thank you all.
Yep.
The next thing you'll hear from us is for the hackathon, which we hope you now all have the tools to build great things in. But otherwise, for the time being, thanks all for joining. Jay, thank you again, and see you all very, very soon. Cheers.
Later, everyone.